this e-learning module, we'll examine the core process involved with servomotor sizing. Sizing is the process of selecting the best motor for a given application. There are many factors that are used to determine the best motor. Some of the factors that determine the best motor are listed here. The motion profile, along with the system inertia, determine the speeds, accelerations, and torques that the motor must be able to produce. Regeneration capacity must also be considered. These factors must be balanced against others such as cost, encoder resolution, environmental ratings, power requirements, or limitations in available space. While all of these factors are important, the core process in servomotor sizing involves 4 key factors. Given that the inertia ratio and motor speed are appropriate for the application, both the max torque and the RMS torque must lie within the motor's capability. The remainder of this e-learning module will discuss this process in more detail. The first key sizing factor is the moment of inertia ratio. The entire moment of inertia in a servo system can be divided into 2 parts, the motor inertia and the load inertia. The moment of inertia ratio is the load's moment of inertia divided by the motor's moment of inertia. Any rotating object has a moment of inertia. The moment of inertia is a measurement of how difficult it is to change the rotating velocity of that object. When sizing, the moment of inertia is often written with the letter J and is commonly referred to simply as inertia. The motor inertia, Jm, is part of the design of the servomotor and is listed in the catalog. However, the load inertia, Jl, often consists of many components. Each component that is moved by the motor contributes to the total load inertia. The total load inertia is found by using the proper equations for each component. Inertia ratios around 5:1 are typical for many applications. Performance tends to go up as the inertia ratio is lowered, often down to 2:1, 1:1, or lower. But when high performance isn't as critical, ratios of 10:1, 100:1, or even higher are not uncommon. In general, ease of control loop tuning and machine performance go up as the inertia ratio goes down. So if all other factors are equal, a lower inertia ratio is better. However, an excessively low inertia ratio can also indicate an excessively large and therefore expensive and bulky motor with little performance increase. If inertia ratio is the limiting sizing factor, it pays to fully understand the application's performance requirements and choose the inertia ratio accordingly. Several motors that provide a suitable inertia ratio may be available. So the task remains to find the smallest motor that still has the ability to produce the speed and torque required for the application. A motor's speed and torque capability is described in the catalog using an individual speed-torque curve for each motor. The speed-torque curve shows the motor speed on the vertical axis and the motor torque on the horizontal axis. First, notice that the speed-torque curve has 2 regions, continuous and intermittent. If the combination of torque and speed required by the motor is found in the continuous region, then the motor can produce that torque and speed forever without any chance of overheating the motor. If the combination of torque and speed produced falls in the intermittent region, then the motor can only produce that speed and torque for a limited amount of time. If that time is exceeded, the motor will begin to overheat. To prevent damage due to overheating, the amplifier automatically disables the motor and enters an alarm state if the time limit is exceeded. But when short bursts of high torque are required, such as during acceleration and deceleration, the motor can run in the intermittent region safely, producing as much as 3 times the rated torque for 3 seconds or longer. The application's RMS torque, however, must lie within the continuous region. If any combination of speed and torque required lies outside both the continuous and intermittent region, then the motor is not capable of producing that combination of speed and torque. When selecting a motor, it is imperative to ensure that the speed-torque curve is used effectively. The speed-torque curve displays several points of interest. Rated torque is the maximum torque the motor can produce continuously at rated speed and lower, and is limited by motor heating. This rated torque is given the value of 100% torque. Likewise, rated speed is the highest speed at which rated torque is available. The motor can continuously run faster than rated speed, but the torque available drops significantly the faster the motor runs. The motor's maximum attainable speed is listed at the top of the speed-torque curve, and the motor's maximum torque is at the far right. The maximum torque available is generally 3 times the continuous torque and can be applied for 3 seconds or longer. While the motor's capability is described by the speed-torque curve, the application requirements are best illustrated using the speed profile and torque profile. The speed profile is a graphical representation of the motor speed versus time, and the torque profile is a graphical representation of the motor torque required for the machine to follow the speed profile during that same time. This graphic illustrates a typical speed and torque profile required to perform a positioning move for a horizontal actuator with no external forces. The speed increases at the beginning of the move, accelerating to a traverse speed, and then decreases, decelerating to a stop. Due to its shape, this is referred to as a trapezoidal speed profile, or a trapezoidal move. The torque at the beginning of the trapezoidal move is highest because mechanical friction must be overcome and because the load must be accelerated from rest. This point of highest torque is called the max torque. Once the traverse speed is reached, a nominal level of torque must be applied to overcome friction and maintain speed. To decelerate the load, often a reverse torque is required. The reverse torque during deceleration is not as high as the forward torque during acceleration, since friction also helps decelerate the load. And when friction torque is high, a forward torque may be required during deceleration so that the motor doesn't slow down too quickly. It is important to ensure that the motor can produce the required max torque at the application speed. The max torque at application speed ideally falls within the intermittent region of the motor's speed-torque curve. It can also fall within the continuous region, but this may be an indication that the motor is oversized. Another torque calculation is critical for sizing, the RMS torque. RMS torque is a time-weighted average of the torque during a complete machine cycle, and represents an equivalent steady-state torque level. For example, a servo motor with 1.2 Newton-meters RMS torque will experience the same heat rise if it produces 1.2 Newton-meters constant torque. So it is also important to ensure that the RMS torque at application speed falls within the continuous region of the speed-torque curve. Provided that the inertia ratio, speed, max torque, and RMS torque all fit the motor as described, then the motor is properly sized. However, a multitude of other factors must also be considered depending on the specific requirements of the application, and may require a slightly larger or smaller motor to be used. This concludes the Servo Sizing Part 1 e-learning module.